Thanks for coming to my talk. Before we get really into this, I have some disclosures to make. First of all, I received research funding from GE Healthcare. That funding is for parallel imaging, which is the topic of this talk. This talk is also pre-recorded and posted on my YouTube channel, so if you really like it, you can go back there and see it again. But also in this world of remote work, I'm presenting this from home. If you hear my dog in the background, I've done a bad job of editing this video, but I'm recording the video so that you don't hear the Labrador of Science trying to give his part to this talk. Beyond that, I do have financial ties to a couple other imaging companies, but they're not related to this work. I'd like to take a second here at the beginning just to thank everyone involved with the work that I'm going to be presenting. Emory and Simpada both have done a tremendous job of acquiring the data, helping queue things up and run stuff on the Research Computing Center hardware. Kevin and Tugan in the CIR and the physics team have been outstanding folks to bounce ideas back and forth with. Tugan did a great deal of work on some of the parallel imaging hyperparameter optimizations that I'll be talking about. I'll take a second here to acknowledge the machine learning work group that's here. If you haven't heard about it, it's a group of us researchers across all stages trying to learn machine learning so that we can stay relevant in the field. We meet every other Monday. If you're interested in joining us, we really appreciate having a broad level of material that's in there and a broad level of interests. So drop me a line and we can talk about it a bit more. Of course, I want to thank the GE Healthcare Neuro team, Suchi, Balin, and Graham. I don't have Shiv on there because I think he's in the MSK team, but he's been doing a really great job of helping us. And then finally, I'd be remiss, I believe I'm the first seminar after Raman has indicated that he's stepping down as the department chair. And want to thank him for doing all that he has to make sure that biophysics is an outstanding department here at MCW. And thank him also for allowing the social part of science to continue in this pandemic by facilitating these presentations and allowing us time to talk with each other about science. So with that idea of the social aspect of science and our human nature of sharing stories around campfires through our evolution, welcome to my campfire. I hope there are a couple goals here that I hope everyone takes away from this. First off, to help share an understanding of what modern parallel imaging technology looks like in MRI, how it works, and how we're using it, and the various different flavors of it. And then the second thing is to start talking about the idea of characterizing the opaque black box that drives this technology. Taking a look at the knobs that one can twist inside of those algorithms that most people don't twist, and talking about the idea of optimizing those knobs for the very specific common technology that we use in our research studies.
Okay, so let's talk a little bit about parallel imaging. First of all, why we need it. And what it comes down to is MRI is slow. If you consider general medical imaging, a head CT is done in the order of seconds. If you have a patient who's in dire need of assessment or somebody that's moving around a lot, you can send them down to a CT and get very good quality diagnostic data very quickly. Downside of CT, of course, is the ionizing radiation and the fact that you don't get as many rich contrasts that you do get with MR. But if you try and do that same sort of acquisition, same sort of resolution with an MR acquisition, you're going to be talking about an acquisition that's in the order of minutes. So there's the big hurdle. If you have somebody that's moving, if you have somebody that's in acute need of diagnostic imaging, MR is still a bit of a challenge. Beyond that, as we go into the research world, many acquisitions take a lot of time just through the way that they work. If you consider fMRI studies, which so many people here at MCW do, you acquire a time series of images to watch the blood response in the brain as somebody's performing a task or resting inside of the scanner. To get those images, one, you need a long time series where that person is doing the activity or resting. You can't really control that. But you need to image at the temporal scale that's on the order of that hemodynamic response function that they're trying to image with fMRI. That hemodynamic response function is on the order of seconds. So you want to be getting that full brain coverage in about 2 seconds at most to catch that blood response. So you have 2 seconds to image that whole brain. And when you're trying to image that whole brain, of course, you have to decide what sort of spatial resolution you're going to acquire. And that resolution decision is pretty much predicated on how much time you have to image it. Before the parallel imaging stuff that we're talking about here was invented, people were pretty regularly getting about isotropic 3.75 millimeter or isotropic 4 millimeter resolution voxels in that 2 seconds for those fMRI studies. For diffusion studies, these are the acquisitions that people are using to measure out the orientation of white matter throughout the brain. And the way you do that is you acquire images that are sensitized to diffusion in a whole bunch of different directions. Each image is sensitized to this diffusion in a particular direction. And when you get a whole bunch of those images, thousands of them, you get to this point where you can actually statistically identify the probability of water diffusing in one particular direction, namely along those axons in that diffusion acquisition. So here, again, you need that whole brain imaged. But you need thousands of images to get that statistical probability map of the direction that the water is going to be diffusing. And then finally, of course, cardiac imaging is a tremendous case for where the parallel imaging has really taken off and been necessary. Here you're dealing with a patient that's moving, or at least a part of a patient that's moving, at least you're hoping they're moving. So your acquisition needs to be fast enough to freeze frame that motion. So the next question is, why not just focus in on that area that you're imaging, that you care about, for MR acquisitions? If you can get away with only, say, 20 or 30 lines, why not just acquire those 20 or 30 lines of the images that you care about? So here's an example offering an explanation as to why you're not seeing that happen with MR generally. So there, if you have a whole brain, but for one reason or another, you're really only interested in anatomy that's up here in that back half of the brain. If you're looking at that, then why not just zoom in your acquisition to hit only that area? To get a spatial resolution of say, 1 millimeter per voxel. If you're talking about this whole field of view, maybe you're talking about 25 centimeters, and here you'd only be interested in about 12 and a half centimeters. So then you can do an acquisition that only has about 125, give or take, voxels in this direction, rather than, say, about 250 voxels in this direction. Well, if you end up doing that, you'll run into the issue of Fourier encoding. And through the math that we use for encoding these images, we're actually not encoding the image itself, but the Fourier transform of the image itself. And when you do that, you're making an assumption that the image is periodic. In other words, when you see this image here, mathematically you're assuming that this image is here, and then if you were to extrapolate it out, there'd be another copy of the image up here, another copy of the image down here, and in fact another to the left and to the right, in some sort of infinite grid of repeating images. So when you just zoom in, that infinite repeating grid actually ends up contracting. And when it contracts, you get this thing called fold over. So here what you see, if we zoomed in, if we tried to do a region of interest that was just around the middle of the brain, you end up with that region of interest around the middle of the brain, but you get the front of the brain wrapped around and overlapping the back, and the back of the brain wrapped around and overlapping the front. So ultimately, you're limited as to what sort of field of view and what resolution you can have based upon the geometry of the object that you're actually imaging. You have to catch all of the object, otherwise it wraps around, folds over back onto the image that you're trying to acquire. So that's why these MR images are generally, although we're only worrying about a small region of interest, catching the whole anatomy. And when you do that, catching the whole anatomy, if you need a high resolution for that small area, you're actually going to need to acquire data to get that high resolution over the full set of anatomy, and that takes a whole bunch more time.
All right, so we've been talking about parallel imaging. What actually is it? And the idea is pretty simple. One is doing the Fourier encoding. You're assuming that you can just use the magnetic field itself to encode the spatial position inside of that image you're trying to reconstruct. With parallel imaging, the idea is that you acquire this data in parallel across multiple different RF receivers. And those different radio frequency receivers are located at different areas around the object you're imaging. So you have a whole bunch of antennas around what you're trying to image. So here, if you have some brain that you're trying to image, you have a whole bunch these straight lines here accounting for different antennas that you've put around that head, different parts of the RF coil in these acquisitions. And if you look at the signal that you get from one particular element of that coil, you'll find that the signal is brighter near that coil and it falls off the farther away you get from it. And with knowing the spatial locations of these coils, and knowing that that signal drops off as you move away from them, there's actually spatial information associated with each one of these coil images that's different from the other coils. So you can use then the spatial information from those coils to get around this idea of having to follow that Nyquist speed limit for Fourier encoding, requiring that you fit that whole object into the field of view. We can get through this with a little thought experiment, and in fact, it actually was the first parallel imaging method that was defined. I'm going to show it in a head here, but it was actually used in the spine, and that idea is using a bunch of different RF coils that have spatially independent receive fields. So if you have this object, and you have some point A and some point B, that when you do your accelerated imaging, of course, fold over onto each other. Say if you did half that field of view, this B here at the back of the brain would fall over onto A there at the front of the brain. Well, let's say you have an RF coil up at the front of the brain that's sensitive to exactly half the volume, and then you have another RF coil at the back that is sensitive to exactly half that head. So that front image would get you that front half of the brain, and because it's not sensitive at all to any of the signal that's in the back half of the brain, there wouldn't be anything that folds over there into the front half of the brain. And conversely, if you look at that signal coming from that coil in the back half of the brain, you'll get that signal from the back half of the brain, and that front half, again, it's all zeros because the coil is not sensitive to it, so when it folds over, you're just getting zeros on top of it. So here, with these spatially independent coils, you're assuming that you still have that periodic image, but it's periodic on a smaller scale that you're getting from that skipping those lines, going a little faster. But those coils are sensitive such that they're not sensitive to anything that's outside of that area that doesn't get aliased. So if you have those two coils for the front and the back, and you know their coil sensitivity is going to 0 after you pass that halfway point, you just cut off those 0 points. You have those two, the front image, the back image, and you stitch the two of them together, and you get the output image. As I said, this is what was done initially for this technique called pills. Now, if you look at it from that perspective, you can actually start creating a series of linear equations. This aliased quote-unquote image that we're getting here from the front coil is that coil sensitivity, in this case 1 times the underlying image at that location A, and then the coil sensitivity at location B, which is 0, multiplied by the image intensity at that location B, and convert, alternatively, with this back coil, it's 1 in the back of the head. That coil sensitivity is 1 there at that location B, and 0 up here at that location A. So in fact, with 1 times intensity B plus 0 times intensity A, which gives us just that intensity B here, because that A location is multiplied by 0. But in reality, of course, most of our coils aren't spatially independent like that. Here you can imagine that we have 4 coils, 1 at the back, 1 a little towards the middle, another 1 towards the middle, and 1 at the front of the brain. And again, if you do that twofold acceleration, you get different levels of aliasing that's dependent upon the sensitivity of that coil. So here, with the coil that's at the back of the brain, you have a nice bright signal from the back of the skull, and almost no signal there coming from that middle part of the brain. Still some. So there now we have this coil intensity A is non-zero, and then we have some small amount of the image intensity at A there, plus the whole bunch of sensitivity from coil B, from the coil at point B, with times the underlying image intensity at point B. As you go through the different coils, looking at that same location, you have different coil weightings there. So it's just a problem of linear algebra now. We have 4 equations and 2 unknowns. The 4 equations are the signal intensities from each of those coils. And the 2 unknowns are the 2 aliased underlying image intensities, that IA, IB. When you solve that out, of course, you can get those 2 unknowns from that series of linear equations. You can solve that for every point over your image. When you do that, this is actually called sense. And that is one of the main reconstructions that's out there for parallel imaging. Now, sense in image space tells us something that we can do in the Fourier space, where we actually do the signal encoding. I'm doing this without showing equations because I don't like equations, or I don't like talking or showing equations. But I will talk a little bit here about the Fourier theory, and specifically, as I said before, we're encoding the Fourier transform of the object we're imaging. There are different properties of the Fourier transform, and one of them is called the convolution theorem. The idea of the convolution theorem is that if you do a multiplication in one space, say image space, and you take the Fourier transform of that, that's the equivalent of doing a convolution, or moving a kernel around an image and sort of replacing one pixel with some set of weighted average of the pixels around it in the other space. So as I said, in the image space, we're talking about having some coil sensitivity, let's just call it like this, multiplied with your underlying image intensity to get your individual coil images. Well, here we're talking about a pointwise multiplication in image space, which through the convolution theorem becomes a convolution of the Fourier transform of the image with the Fourier transform of that coil sensitivity map. So what we have here is just a convolution here in K-space to get that coil image, and you can get a Fourier transform of that convolution and get that equivalent coil image over an image space. With that known, the idea came up to, instead of doing sense in image space, to do something called GRAPPA in K-space. So the idea of GRAPPA in K-space is that as we're doing this acceleration, we're not actually acquiring every line of the image that we're trying to reconstruct, right? We're getting that aliasing. You get that aliasing by acquiring essentially every other line. So having that every other line sort of acquisition, you'd be acquiring those dots here that are dark and skipping those dots that are open. So you have these points here where you have actually skipped the acquisition, and you can use this convolution theorem in the K-space, in this Fourier space, to interpolate what those observations should actually look like. You acquire this auto-calibration signal. In other words, you acquire some chunk of data where you aren't skipping lines, and you figure out to reconstruct, say, this kernel here in the this pixel here in the middle of the K-space array. It's some weighted average of those pixels around it, which is actually coming through the Fourier transform of the coil sensitivity map itself. So you're taking you're essentially modeling what that coil sensitivity map is, not in image space, but in this Fourier space. And then based upon that model, taking where you have these observations and figuring out what the skipped observations K-space, Fourier space values actually should be, putting them into that array, and then going ahead and just doing your standard Fourier reconstruction from that frequency space, and you end up with an unaliased image. Computationally, this works out relatively nicely. You only have to solve the inverse problem for those coil sensitivity maps for that calibration region. So again, if this is the linear model that you're fitting here, in sense, when you're doing that image space, you're fitting a unique model for each point of the image. Here in the Fourier space, you're actually collapsing that down, so you only need to solve that set of linear equations once to do this interpolation. It works out quite well, and in fact, this is what's used pretty much across the board now in modern accelerated acquisitions. So just in terms of takeaways here, MRI is slow, and it really gets to be more of a problem when you're acquiring thousands of images, either for functional imaging or diffusion acquisitions. There are Nyquist limits that make you acquire enough lines to actually fit the object that you're imaging into this field of view that you end up reconstructing. If you break that speed limit, you get this aliasing or this fold over of the data onto itself and get bad images. If you try and make those acquisitions faster by just getting more lines with each acquisition, that causes problems like geometric distortion and blurring. But all hope is not lost. Spatially varying coil sensitivities can be used beyond that Fourier encoding to spatially encode your data. And then it's just some linear algebra afterward to reconstruct non-aliased images in the either image space or Fourier space. So to this point, we've been talking about acceleration by skipping lines in that K-space, getting that smaller field of view to get that faster acquisition. That's been pretty much driving technology. Around the turn of the century, it came out, and there's been tweaks on that over the years. But there was actually a quantum step forward with simultaneous multi-slice imaging. And that really came forward with the Human Connectome project. They were calling for, in about 2010, 2011, this huge request for applications that was looking for existing but cutting-edge non-invasive imaging technologies to be optimized and combined to acquire structural and functional in vivo data about axonal projections, neural connections in the brain across hundreds of healthy adults. And it got people's attention. They were talking about a 5-year study, $6 million per year. So that got a lot of folks thinking about how to actually improve fMRI acquisition to go beyond that spatial limit that people were seeing at that about 3 3.75 to 4 millimeter resolution. But as it says there, right, existing but cutting edge technology. Which takes us to everything that was old becomes new again. And if you look back to the early days of MR, 1988, Gary Glover and folks over at GE here, no, actually ASL in New York, were looking at this idea of acquiring multiple slices of the object that we're imaging simultaneously. So instead of getting acceleration by getting aliasing as the data gets folded over on itself, they were talking about taking multiple parallel slices and acquiring those slices and getting them to alias as they would reconstruct as they were on top of each other. Now, back in 1988, these arrays of RF coils for acquisitions were not in existence. So they used something called Hadamard encoding, where they would actually acquire the data multiple times, just with the magnetization phase in those slices pointing in different directions each time. And then you could get some better quality images, essentially averaging for free, if you added and subtracted those images appropriately from each other after you reconstruct them. We'll talk about that a bit more here in the near future. Now, though, so this idea was out there of doing multi-slice acquisitions. As I said, the parallel imaging technologies had been developed around the turn of the century. So multiple labs developed the simultaneous multi-slice acquisitions for fMRI and diffusion. The folks that won the race were over in Minnesota with Steenmoller. And ultimately, they received one of the Human Connectome Project awards with this work. In parallel to them, we also here at MCW were working to develop something similar. We got the same data into our, or similar data into our application. But there the idea was, again, to acquire multiple slices simultaneously so that they end up aliased with each other, not in that phase encode direction from skipping lines, but in that slice encode direction where they were acquired just with RF pulses that excited those at the same time, and then use the math of parallel imaging that had been defined to separate out those images, not having to do that multi-shot SIMA acquisition that Gary Glover had developed. So what does it look like? Essentially, you're acquiring one slice with traditional methods and multiple slices simultaneously. So you build up that volume here by acquiring one slice at a time in an interleaved fashion traditionally. Or if you acquire multiple slices simultaneously, you see that you can build that whole volume out much more quickly by doing that parallel imaging in that slice encode direction. In comparison to those techniques where you skip lines, you actually end up doing a bit better with simultaneous multi-slice acquisitions. You get those the temporal overhead associated not only with the readout, but with the excitation pulse, with the fat saturation, with the end of the acquisition crusher gradients. All that stuff is amortized across each and every one of those slices that's acquired simultaneously. This has become the de facto standard. So slice leakage is a fancy word for residual aliasing. When you perform the slice GRAPPA, you're optimizing to get a highest correlation between your unaliased k-space and your reference k-space. It's not doing anything about making sure that when you apply one slice GRAPPA kernel for unaliasing one slice, it doesn't bring other elements of the other slices that were acquired simultaneously into it. With fMRI and with diffusion tensor imaging, that leads to residual aliasing that can bias your results. You can end up with artifactual correlations between slices with rest, and you can end up with essentially an apparent leakage or contamination of fibers in one voxel with those of the aliased voxel. A group has come out with a more advanced sort of GRAPPA fitting kernel, where you're minimizing not only the reconstruction error, but also minimizing that leakage of one slice into the other slices. And that has, again, become pretty much the gold standard these days for the slice unaliasing algorithms. Now, it's not the only solution. And with deep learning taking a forefront of what's going on in the field these days, Steenmoller and his group came up with this idea of RAKI, in the tradition of MR acronyms. Yes, that is a wonderful liquor. But it's a very shallow convolutional neural network, which essentially replaces the idea of that GRAPPA kernel. So it's like GRAPPA, fit for each and every acquisition. So instead of doing a linear fit of GRAPPA kernel weights, with RAKI, one is doing a nonlinear fit of this convolutional neural network to perform that GRAPPA convolution. Because these convolutional neural networks deal with real valued data, the complex valued MR data just essentially gets stacked up on top of each other. So if you have a 32-channel coil, you end up with 32 real channels and 32 imaginary channels in that first block of convolution, which here gives you that 64 layers. You deal with convolutional kernels here in this case of 9 by 9. And if you have, say, 104 by 104 k-space matrix, you have that. And then the RAKI network is essentially one convolutional layer followed by another convolutional layer, both with the same 9 by 9 kernel sizes. Then a 1 by 1 convolution with 128 kernels. And then one more 2D convolution with those 9 by 9 acquisitions, and outputting then a real and imaginary channel of k-space. So this was the originally what was designed as RAKI, and with RAKI, one works with usually just like with GRAPPA, your alias data set and your unalias data set. So your alias data set is essentially the sum over k-space across all of your slices that are simultaneously excited, and your unalias is that single reference image. What we have done as a means of improving this is in the world of deep learning, it's called data augmentation. Essentially, adding diversity to our training data. What one can run into when you're only using one or a very small number of training data sets with so many variables to fit in this convolutional neural network is overfitting. You can get output images that look just like your input images, but you lose that temporal variation, or if you have contrast differences like you have with diffusion acquisitions, you lose that contrast difference, and you actually get worse dynamic data, but really stable temporal means that look just like your training data because you've overfit it. So what we've done is we've actually acquired single slices for our reference data of each of those slices that are excited in the packet, and then artificially create alias data by summing subsets of those slices for our training set. So if we have 8 slices, say, one is just the sum across those 8 slices. Another piece of training data would be each one of those slices being non-zero, being that acquired data, and the other slices all being 0. And the idea is, if that slice that we're trying to unalias here, slice 2, is included in that training set, you create that sum, it goes through the neural network and outputs the k-space for that single slice. Similarly, if you have all 8 slices, you sum all 8 slices, run them through the convolutional neural network, and again, you're trying to get that one slice unalias, that slice 2 again. If you create a data set here where you have data in all of the slices except for that slice you're trying to unalias, the output of this convolutional neural network should be 0. So as we put this in as our input for our training data, we put zeros for our output. With 8 slices, this gives you 256 training data sets. It really diversifies how much data you have versus the one training data set, which you'd have with standard RAKI. Now, before I really dig into the RAKI stuff, I want to talk about slice arc a little bit, and this idea of what are called hyperparameters. They're not parameters that are all crazy and move around, although that's kind of a fun animation. But these are things that these are knobs that one can tune on the reconstruction algorithm. These are the sorts of things that hide in black boxes, and that people generally use the defaults that have been created over time. And those defaults are generally identified for individual, or rather not individual, but for groups of data. What on average is good. Now, we have with research very specific protocols that we're running across a large number of patients and participants. One can take a look at those little knobs and tune them up specifically for those acquisitions that we're worrying about. And that's one of the pieces of work that we've done with GE here. Again, getting out of that folklore of using what's there and what people have thought to be good in general, digging into that and identifying what's really ideal for a particular set of acquisitions. So what are some of the slice ARC hyperparameters, or slice GRAPPA hyperparameters? So if you have some case space, like you would over here in this grid of observations, you can look at a few different things. First of all, what data should you use to fit that slice GRAPPA kernel? Should you choose this data here in the center of case space? Maybe something that's really in the center of case space, going out a little more in the Y direction, a little less in the X direction. Should you be looking at data in the edges of case space, the early edge of the case space, the later edge of case space? There's a whole bunch of different options that one has here. And there's some folklore, and there's actually conflicting literature about how well your GRAPPA kernels do if you're fitting in the center of case space to the edge of case space. The spoiler here is that generally the edge of case space, you get better results than if you fit in the middle where you have more signal, which seems a little counterintuitive. Conversely, if you're fitting those kernels, what is a good kernel to fit for that GRAPPA? Is it a nice symmetrical thing that's nice and small? Is it something that's asymmetrical, getting more observations in that X direction, or how about the Y direction? Altogether, again, people have played around with these things individually and come up with some suggestions as to what generally works. But when we're doing these acquisitions for the Human Connectome project, there really do seem to be some good solutions that perhaps we should use regularly when we're doing those acquisitions and tailoring the reconstruction for that. Beyond that, right, what RF coils should you use? We have a whole host of them with different properties, different sizes, different numbers of channels. What's best for the acquisition and what's best for the participant's comfort? Is there a trade-off that one needs to worry about? When you're performing the fit, the idea of regularization in performing the fit is a big deal. So how much regularization should you have? And again, in general, the question here is, what's optimal for a particular study with a particular set of acquisition parameters? Is it what people are choosing as the default? Or is it something that's a little less obvious? With SliceArc, there are a whole bunch of different hyperparameters that one can worry about. And we talked through a few of them on that previous slide here. But what we did is we took 5 subjects, scanned them with a whole bunch of different multi-band simultaneous multi-slice accelerations, including the Human Connectome project acquisition, which people really like using, and reconstructed every data set 27,216 times. And we did a true grid search of the horizontal calibration region, the phase encode calibration region, the kernel size and the frequency and phase encodes. Coil compression, essentially a data reduction factor prior to fitting the GRAPPA kernels. The regularization parameter weight, the multi-band simultaneous multi-slice acceleration factor, and what coil we used. A big shout out here to the MCW Research Computing Center. This 27,216 reconstructions across 5 subjects. We're talking well over 130,000 reconstructions. On my desktop, this would have taken years. On the Research Computing Center, it took about a month. So again, MCW's high performance computing really shone through here and enabled us to do a systematic review of how these knobs are best tuned for these different acceleration factors. So then we have some results that come from it. looking at the slice arc hyperparameters, you saw all of those different things that we looked at. It becomes a rather high dimensionality data set. So what we did to consider how well each method reconstructed, we took the correlation of the image that came out of that reconstruction with respect to the single band acquisition. Correlation of 1 means that the multi-band reconstruction and the single band reconstruction worked out great. Correlation of less than that indicates that it didn't work out so well. So radially here on these radar plots, we have the correlation coefficient here in this one going from 0.6 all the way up to 0.96. Along as you go through the angles here, we have the coil compression, so all coils versus 8 virtual coils, 16 virtual coils, and so forth. The marker shape indicates the dimensionality of the Y kernel, and the marker size indicates how much of K-space was used for that Y kernel fitting. Interestingly, as we went through the data, there was almost no difference in ARC when you were looking at those X components. That comes down to the algorithm, I believe, where they're actually performing a Fourier transform in that frequency encoding direction prior to fitting the ARC kernels. But that's an interesting thing here, nonetheless. Regardless, as you can see from these example images from data sets that were acquired with those markers, when you have radially outward, you have really good image quality with your reconstructed images. And when you have very little radial distance, you can certainly see some residual aliasing in those reconstructed slices. In our paper, we have a bunch more of these plots, but folks tend to be interested in pushing the limit. And when you push the limit, you see the most differentiation between the different parameters that you use. And what you have here is for the 32-channel coil with an 8-band multi-band factor, and the 48-channel with the high multi-band factor. And interestingly here, lower regularization generally yields those blue markers to give worse results than higher levels of regularization. Not exceptionally surprising. One of the more surprising things, though, is that as you're fitting the GRAPPA kernels or the ARC kernels, those squares and stars end up doing the best. So having a smaller kernel compared to the larger kernels is a good thing with these acquisitions. Similarly, the calibration region ends up being the median, if you will, the middle size tends to do best. One other thing to look at here is that as you go through the coil compression, you're getting pretty good results, even if you're only using half of the channels that are available. So 16 virtual channels, you end up out here with high correlations versus with all channels. Similarly here with the 48-channel coil, once you hit that 24 channels, you're out there at that farthest ring where you're getting good results and having much less computational burden. With an exhaustive grid search across the parameter space, we can look at interactions between different variables. So in this case, let's just go ahead and take a look at that kernel size in the Y direction. And what you'll find with that is that with smaller kernels here in the blue and the red lines, you can get away with smaller calibration regions and still do very well. But when you go to larger kernels, you have more unknowns in that kernel that you're solving, and you end up needing those larger calibration regions to fit that. Similarly, with fewer parameters that you're trying to fit in those smaller kernels, you can get away with less regularization with it. And you can also get away with a fewer number of virtual coils to get some good results. Now, the next thing I'm going to talk about here is slice RAKI. This is that deep learning reconstruction, and again, we're going to talk about the various hyperparameters are there with it. Similar to the slice GRAPPA or the slice ARC, you have these various things to worry about. You can worry about the kernel size, but also you have these other neural network variables. The number of convolutional layers that you have going through it, the number of these unity-sized filters, the inclusion of batch normalization to reduce some drift of the parameters, and the idea of training dropout. You can have training dropout or not to reduce the probability of overfitting data. Now, deep learning does have a whole bunch more hyperparameters. As we looked through these various elements that I just listed here, there are a number of elements that really can't, or that we decided not to vary. So, for instance, the types of activations that we were using. We here use the rather standard rectified linear unit for the activations. We also use the rather standard atom optimizer with actually default learning rate and decay parameters. One thing that we learned as we were doing these convolutional neural networks is that bias terms are bad when you're doing these convolutional neural networks in k-space. A bias can lead to a DC offset in your reconstructed k-space, and that DC offset after the Fourier transform gives you a nice bright pixel in the center of your image. So we kept the bias terms out of this. We did just a standard absolute error loss function. So we were computing our convolutional neural network to create an output k-space, and we're looking at simply the absolute value of the difference between that k-space and the ideal k-space. To keep things on fair footing, we kept ourselves to about 5 minutes. Well, we kept ourselves to 5 minutes of training for each network. You need to keep it short here because the idea is that with RAKI, again, you have to compute these convolutional neural networks for each and every patient. And that takes a lot of time. It can take a lot of time. A lot of the main networks that are out there are trained for days. Here we're looking at training each of these for 5 minutes. And that's 5 minutes on what we had in the Research Computing Center, the NVIDIA K80. We did do a couple of these reconstructions on newer Volta model GPU. And there we saw that we could get about the same number of training epochs in just about 3 minutes. So with newer technology, of course, this can either go to faster training or more training to get us good results. With the RAKI acquisition, we used human connectome harmonized protocol for fMRI. Here we use a Fourier auto-calibration rather than a Hadamard auto-calibration. It's the same idea of varying the phase over time, but instead of doing additions and subtractions, you do a Fourier transform through time. We changed that to more or less play nicely with the community as the Fourier technique has really sort of taken off. The testing data, we did not reconstruct the whole time series because there was not really a point in doing that. But we took 20 equispaced time points throughout that whole 5-minute time series. Taking equispaced points gives us a little ability to look at how this the system can drift over time if the patient moves or if the field drifts. And of course, that testing data was all not included in the training data. To look at the various hyperparameters, we had a few less here than we did when we looked at the slice ARC parameterization with about 3,072 networks with values, as you can see, that are here. And again, we did this on 5 prospectively consented participants. The results of this, instead of those crazy web plots that I had shown previously, we'll just look at some violin plots. So as you look at the number of layers in the convolutional neural network, we have the networks trained with white without the split slice augmentation, so without just using that one data set for a reconstruction or training, and with that split slice augmentation. So that's with that 256 training set. And as you can see, the networks perform pretty evenly here. In fact, the non-split slice version works very well with just one layer. That one layer is, when you think about it, just a degenerate case of standard slice GRAPPA. So that's interesting. With a single layer, as you would get in slice GRAPPA, you get better results than if you augment that training data. But as you go to higher numbers of layers, you get to the slight improvements. These dashed lines here are the medians of the results. Lower is better as we're looking at that absolute error loss function here. So with moderate number of layers, the split slice training tends to work. When you go to higher numbers of layers, again, you start seeing some divergence with the split slice GRAPPA, split slice augmentation starting to perform a little worse. Again, as you look at filter size, it's very much the same story. As you go to more and more filters, you're doing better with that split slice augmentation because of the fact that you have more unknowns with more filters, and you do better with more data for that training. With the number of filters per layer, again, the trend goes in that way of suggesting that you're doing well when you're using the split slice training augmentation. And if you have 64 filters per layer, you end up pretty much hitting an asymptote. You're generally good at that point and giving a little overkill if you start going into higher numbers of filters per layer. Looking at the number of single filters in that second to last layer, again, if you get to that 128, you hit an asymptote of how well the network is working. And again, the split slice augmentation works out pretty nicely. As you look at these tails, they do narrow up as you go to more and more filters. Batch normalization generally improves the network performance. So as you're going through the training, if you renormalize your data every time that you try and fit that convolutional kernel, you do better. And dropout. This one ended up being relatively interesting. Without dropout, the split slice GRAPPA does split slice augmentation for RAKI does very well. With the standard RAKI without that split slice augmentation, it doesn't do so hot. But when you essentially drop out half of the elements that you're trying to fit on each pass through the neural network as you're doing the modeling, the split slice augmentation does far worse. And conversely, the standard formulation of RAKI does better. And this seems a little counterintuitive until you take a step back. The purpose of training dropout is to reduce the overfitting of your data. When you have just one data set that's being used for the training, you're going to overfit that data. Even if you're only working in 5 minutes, it's continuously working on that one data set. If you include the dropout, you avoid that overfitting, or you reduce that overfitting, and do better. Now, with the split slice formalism, we have that increased factor of 256 times the training volume. With that increased training volume, you run into less of an issue with overfitting. And in fact, when you include the dropout, you're working with less of the model each time you pass through doing the fit. And that causes the model to not fit as quickly and as robustly, leading to a reduction in performance. Finally, we have some conclusions to talk about. With the slice arc, there is a set of best performing hyperparameters for those connectome sorts of acquisitions. In terms of computational time, we do best with smallest frequency encoding filter and calibration regions. And we don't get much of a, we get no benefit from really changing that, so might as well save the computational time. We do well with the minimal phase encoding filter size, with that through slice aliasing rather than that in-plane aliasing. We also receive marginally better results with larger phase encoding calibration regions and moderate regularization. Coil compression is a big thing that we learned here is really useful. You can cut down tremendously the computational load by using half of the possible virtual channels. Finally, that Nova Medical 32 channel coil across the board did better with this splice unaliasing. With RAKI and split slice RAKI, split slice augmentation turns out to be good. And it's a great way to, using this non-linear method, a great way to reduce splice leakage. Interestingly, if you're going to be doing RAKI versus split slice RAKI, different networks turn out to be better. With the split slice training, you use the batch normalization, no training dropout as we talked about, a bunch of layers, larger filters in those convolutional layers, and a low number of single voxel filters. Whereas when you look at the standard RAKI, batch normalization again, but here you use the training dropout, you use fewer network layers, use smaller convolutional filters in those convolutional layers, and you actually use more single voxel filters in that second to last layer. So with that, I'd like to thank you for attending my campfire here. I hope that you got some understanding of parallel imaging in MR. You saw how we're probing that opaque box of the software that's driving modern technology, and in that process of that finding things that we ended up putting out into the prototypes that we've released with those optimal optimizations for the human connectome protocol. That you understand the uncertainty of relying upon black boxes and find that this is a warning here for probing those black boxes and finding that sometimes there are better ways or better parameterizations that we can use. Thank you.